Uh, Thanks, Johannes, for the introduction. Hello, everyone. My name is Kiran. I'm an engineer working in the Fortran compiler team in Manchester, UK. And the topic for my presentation today is Openmp in Flang using MLIR. This slide shows the contents of my presentation today. I'll basically introduce Flang and then briefly summarize the Flang compiler's flow, and then discuss about the support for Openmp in Flang, and what's the plan for code gen for Openmp in Flang. Once I provide a high-level summary of that, I will go into a bit more deeper into each of these stages in the compiler flow, starting from the parse tree representation, semantic checks, high-level IR, and all the way to lowering to LLVM IR. Once I've done that, I provide a status of the implementation, and I end with pointers to how you can get involved if you're interested. As you all probably know, the Flang Fortran frontend was merged into LLVM in April this year. This project started off as the F18 project at NVIDIA in collaboration with the US Department of Energy Labs. ARM, AMD, and engineers from the US DOE labs are contributing to this project, as well as a few hobbies and individual contributors. So there is a small community that has grown around this project. So there are two reasons for coming with a new Fortran frontend. The first one was that the LLVM compiler infrastructure did not have a Fortran frontend. And as we all know, Fortran is very important in the HPC space. So for LLVM to be heavily used and to be useful in the HPC community, we want a Fortran frontend for LLVM. The other reason is that previously or currently also there is an old Flang project that is based on PGI Fortran that has been there for some time. So this is compatible with LLVM IR. With LLVM, it generates LLVM IR, but it has a few issues. One of them being that it's quite old. It's almost 30 years old, and all the issues that come with age is there in this project. And it's not properly integrated with LLVM. Although it generates LLVM IR, it does not use the IR builder. And the response that we got, and also the current engineers' feedback, was that rather than trying to improve the old Flang, it's possibly better to start writing from scratch a new Fortran frontend. So that's how this new Flang Fortran frontend came in. And this new Fortran frontend is built using modern technologies. It's written in modern C++, C++17. It uses the MLIR infrastructure that was recently open sourced by Google. It's important to note that Flang is a work in progress. It's not a fully functional compiler. Although it's part of LLVM, there is still work going on. If you currently invoke Flang, what happens is that Flang performs parsing and semantic checks, and then it unparses it back to Fortran and then searches for an external compiler to complete the compilation. Note that this is just for testing purposes to ensure that the parsing and semantic checks are working correctly. So that was a short introduction to Flang. And this slide shows the whole compiler, its whole intended compiler flow for the Flang project. So that's the flow is shown on the right-hand side. In this diagram, you have a Fortran program, and then there is some parsing and semantic analysis that happens. The output is a Flang parse tree. Then it is lowered into a high-level IR called FIR or Fortran IR. So the idea is that LLVM IR is too low level for Fortran, and it cannot capture all the properties and semantic information in Fortran. And by the time code reaches LLVM IR, you have lost some information. So some of the optimizations are not possible. So having a high level IR, hopefully where all the semantic information is available, we can do more optimizations. So that's all the idea of this high level IR called FIR. So, and in the MLIR layer, it undergoes several transformations, and in MLIR, you call various dialects are there. So finally, if you want to target to LLVM-IR, what happens is that it has to be lowered into a lower level dialect called LLVM-MLIR. And once you reach that, then there's a translation library which takes in this, which when given this LLVM-MLIR generates LLVM-IR. So this is the whole Flang compiler flow that will be finally in place. Now we come to Openmp support. As we all know, Openmp is a very important standard, and it's important in the HPC space and very widely used. The latest published standard is 5, with 5.1 to be announced later this year. Support for latest Openmp standard is also important for Flang to enter production, because the old Flang project, which some of the commercial companies use, has partial support for Openmp 4.5. So in order to replace the old one with this new one, we have to have at least support for 4.5. And because 5 has been around for some time, ideally, we would like to have Openmp 5. So what is supported in Flang right now? Flang supports Openmp 4.5 parsing. It supports some semantic checks. The work is in progress, it's not complete, but it's in progress. And if someone has to use the Openmp with Flang, then you have to use the Openmp flag to enable the Openmp pragmas. Coming to code generation for Openmp, there are two important components that are used for Openmp code generation. First one is MLIR. The second one is Openmp IR Builder. In the next few slides, we go into a bit more detail about these two. So MLIR stands for Multi-Level Intermediate Representation. This is a project that was recently open sourced by Google. It's a new approach for building compiler infrastructure. Basically, you can use it to build SSA-based intermediate representation. It provides a declarative style for defining intermediate representations. It also provides common infrastructure for a lot of common tasks like printing operations, parsing operations for location tracking and parse management. The Flang compiler, because it wanted a high-level IR, so there was some work going on when this was when MLIR was open sourced, and it was an ideal fit for this purpose. So the Flang project decided to use the MLIR infrastructure for defining the high-level IR, and the result is the Photon IR or FIR. So the important point note here is that FIR models the Fortran language portion. So there is no representation for Openmp constructs inside this FIR. So the reason is that you want to keep the Fortran portions as pure as possible, and you don't want to have things which are not inside the language inside this IR. So what we need is a representation for Openmp constructs. So you don't want to add Openmp constructs into the FIR. So what we decided finally is to have a separate dialect in MLIR for Openmp, so that there is a representation for Openmp constructs in the MLIR layer. The other advantages for having a dialect is that if tomorrow clan decides to use MLIR, then there is this Openmp support in MLIR which can easily use it. An important point to stress here is that in MLIR, individual instructions are called operations, and these operations can contain regions. So this is very attractive for Openmp, because we all know that Openmp constructs have regions enclosed inside that. And LLVM-IR cannot have regions inside it. So if you want to represent an Openmp region, then you have to do some kind of outlining. And that's what is shown on the right-hand side. On the right-hand side, you can see on the top, there is an Openmp operation called parallel. And that parallel operation has a region in red, which basically contains an addition operation. And if it has to be represented in the LLVM-IR, then you have to take this whole region outside into a separate function, which is shown below in red, which is called the outline parallel function. And then there has to be a runtime call which calls this. So, so this is another attractive reason for using MLIR for Openmp, that there are operations, and operations can have regions inside it. The second component that is important for Openmp code generation is the Openmp IR Builder. the Openmp IR builder, or if you want to generate LLVM IR, there are basically two important tasks. One is that you have to insert calls to the Openmp runtime. The second one is that you have to outline the Openmp regions into separate functions. So codex is in Clang for these two tasks. So then why build all this again from scratch if we can reuse the existing code in Clang? So Johannes and other engineers came up with this idea about refactoring this Openmp codegen in Clang and moving to the LLVM directory. Basically, they have put it in LLVM lib frontend for Openmp. And once it's there in LLVM, then both Flang and Clang can use this refactored codegen for generating LLVM IR. So yeah, so Openmp IR builder is also used for codegen. So finally, we come to this new flow for Openmp in Flang. If you have a Fortran program, it goes through some parsing and semantic checks, and you get a Flang parse tree. It's lowered into a mix of Openmp, MLIR, and FIR. It undergoes several conversions and finally results in Openmp and LLVM MLIR. Then you use an Openmp IR builder to translate that completely into LLVM IR. So that's the high-level flow for Openmp inside Flang. So in the next two slides, I'll show an example so that this becomes more clear. So in this example, I depict various stages in the compilation flow. On the left-hand side, there's a simple Fortran program, which has an Openmp parallel pragma, and the region inside that has an addition operation. In the middle, what we've shown is the Flang parse tree. I've highlighted in red the areas that we are interested in. There is an Openmp construct, and the directive is called parallel. And inside the region, which is called a block, there is an assignment statement and an addition expression. And this is then converted into a mix of Fortran IR and the Openmp dialect. And that's what we see on the right-hand side. There's an operation called OMP parallel. And then there is a FIR operation or FIR operation called add, which adds these two numbers. And then the next step is to convert this mix of Fortran IR and Openmp into the LLVM dialect and the Openmp dialect. So that's what we have in this slide on the left-hand side. There is a parallel operation, and inside that there is an LLVM dialect operation. There is an LLVM dialect operation called fadd. And finally, we convert this using the Openmp IR builder into the LLVM IR, which we have seen before. There is this for call, which calls an outline function. And inside that outline function, there is an LLVM instruction called fadd, which adds these two numbers. So I provided a high-level overview of the Openmp plan for Flang. Now we will go into each of the intermediate steps in this whole flow, starting from parsing and all the way to lowering to LLVM IR. I just want to check whether you are with me, because I cannot see you and my screen is full of this slide.
We can hear you. We can see your screen.
So far, so good.
Thank you. So the first step in this is to have this parse tree. So there should be a representation for Openmp constructs and parse in the parse tree. So there are basically two kinds of Openmp constructs. One is the executable constructs and the other is the declarative construct. And we have high-level structures for these in the parse tree. So for the executable one, you have the Openmp constructs, and for the declarative ones, you have the Openmp declarative construct. So, as I mentioned before, C++17 is heavily used inside Flang, and one of the use cases is STD variants, which are useful, replacements for union. So what this Openmp construct says is that an Openmp construct can basically either be a standalone construct, an Openmp sections construct, a loop construct, a block construct, an atomic construct, or an Openmp critical construct. And these structures will have further definition. For example, Openmp standalone can further be a flush or a barrier and things like that. Right. So here we have an example. There is a Fortran source on the left-hand side and its pass tree on the right-hand side. In red, I have shown an Openmp flush instruction, and on the right, there is its corresponding representation in the pass tree. There's an Openmp construct, there's an Openmp standalone construct, and this standalone construct is basically a flush construct here. And Flang is, and the ASD for, or the pass tree for Flang is quite friendly, and we can create tools or utilities with this. It supports a visitor class. So if you define a visitor class in the following way, so you would want both two functions called pre and post defined. And for those constructs that you're interested in, if you can define your own specialization. So for example, in this class called Openmp counter, I have defined two generic functions, pre and post. And for the specific thing called Openmp construct, what I'm doing is that I'm incrementing a counter which was initialized to 0. So now if I call this visitor to walk on a pass tree, what I finally get as the result is the number of Openmp executable constructs in this pass tree. So the Flang pass tree is friendly for creating utilities. Next, we come to semantic checks. So, when a program is given, or when a program with Openmp constructs is given, one of the job of the compiler is to ensure that this program conforms to the Openmp standard. So, and that involves a lot of things usually. One is that, only the permitted construct should be there in a clause. There should be clauses which should not exist together. Sometimes there are requirements like if you have a clause called num threads for parallel, it should be a positive integer. Then there are other constraints like, you cannot have a particular construct inside another construct. There are a whole lot of semantic checks that have to be done. In this slide, a small example is shown before the Openmp declares MD construct. So you can see that it says which are the clauses that are allowed, which are the clauses that are only allowed once, and which are the clauses which cannot occur together. In this case, in branch and not in branch cannot occur together. So these are some of the constraints of the Openmp declares MD construct. So the code is written in a high-level way so that it's easy to understand. So we finished the parsing and semantic checks. So the next is to have a representation for the Openmp. So you have to define Openmp operations in a high-level IR, in MLIR. So that is the focus of the next few slides. So MLIR provides a declarative way of defining Openmp operations. It uses the table-gen infrastructure that is shared with LLVM. In this declarative style, we can define the input and output of the operands, whether these operations have regions inside them. And once you have defined all this in a declarative syntax, it automatically generates printers and parsers for printing and parsing these operations. A simple example for the barrier operation is shown in the next slide. So here we have two definitions and a class. So the first one says that you have a dialect called the Openmp dialect, and the name of that dialect is called OMP. So any operation that is part of this dialect will have this prefix OMP dot. And then an Openmp operation has a name, a mnemonic, as well as some properties associated with it. And in the last definition, you say that you are defining a barrier operation, and a barrier operation is an Openmp operation with the name barrier. And below that, some additional information about this operation is provided. Some can be just for documentation purpose, and others can be for describing the input, output, operands, etc. So here you have the summary and the description of the operation, as well as the assembly format. And because barrier does not take in any input operands or output operands, so those are left as empty. But often that is not sufficient. Sometimes for many of the trivial operations this is fine, but for Openmp, where there are a lot of clauses and inside constructs, we typically want some the Openmp construct or the Openmp operation to be written in such a way that people know that, or the domain information, that is the Openmp domain information, is easily transferred into the representation of the Openmp operation. So for that, you would require custom printers and parsers. So in that case, that has to be manually written. Then the Openmp clauses are best defined as in a directive. So like you have Openmp parallel operation, then you want to say that there is a shared clause which can take a lot of variables as arguments, and that's a list of variables. So if you can define in that way, that makes it easier for users to understand. So in the next slide, I have a definition of the parallel operation. This builds upon the syntax that we saw in the previous slide for the barrier operation. Here you have defined a parallel operation as an Openmp operation with name parallel, and it has some properties. As before, it has a summary and a description, but additional things that are coming here is that it has a list of arguments, which are the clauses. It has an if clause, a num threads clause, a default clause, and a lot of things. The other important points to note here is that the types of all these are marked as any type. So the reason for this is that we want the Openmp dialect to be generic and not be specific to FIR or LLVM-IR, or LLVM dialect or something like that. It should work with any of these types. So that's why all these types are marked as any type. Then there is a facility to mark, so most of the clauses in Openmp are optional, so these need not occur always. So these clauses like the num threads and the if expressions can be optional. And then some of these clauses like private, shared, and copy, these can take any number of arguments. So these are marked as variadic. So variadic is 0 or more. And then the parallel operation also has regions inside that. So there is a specification for how you define regions. And then, as I mentioned before, because this requires a domain-specific syntax, we have to define custom printers and parsers. So this functions parse parallel op and print parallel op has to be defined so that you can print and parse it. So this slide shows two examples of the Openmp parallel operation that we have defined in the previous slide, which works with both standard types in MLIR as well as with the LLVM dialect types. So on the left-hand side, you have an Openmp parallel operation, which has the shared clause and the copying clause, and has some arguments in the standard dialect. Nested inside this Openmp parallel is another Openmp parallel, which has an if expression. On the right-hand side, I have an Openmp parallel operation, and it has a num threads clause, and the num threads is specified to be of the LLVM dialect type. There is also another point to note here. There's a clause called prop bind. These kind of clauses are constant. That means that the values of these clauses can never be a variable. So these are called attributes inside MLIR. So here that is specified. The prop bind clause has the value master, which is an attribute. So now we have, in the previous few slides, we have gone into the details about how you define Openmp operations. Now the next step is that once you have this Openmp operation, you have to lower the Flang parse tree into the Openmp operation. I'm not going into much details of this stage, other than just noting that there is some code in Flang in the lower directory called bridge.cpp. It finally ends up calling a function called gen Openmp construct, which is given an argument which is called the Openmp construct. And depending upon the kind of the type, depending upon the real type of the Openmp construct, if it's a barrier construct, then it's the job of this function to create an operation in the MLIR dialect for the barrier operation. So now we come to the final step. Once you have this MLIR, Openmp MLIR dialect sitting it with the LLVM MLIR dialect, you want to translate it all the way down to LLVM-IR using the Openmp IR builder. So in the LLVM dialect, what we have is a list of functions, and each function can have a list of blocks, and the blocks have a list of operations inside it. So that is the traditional flow for lowering from the LLVM dialect to the LLVM-IR. So you have a convert function which calls convert one function, which calls convert block, and which calls convert operation for each operation inside that. The only additional change here is that operations can contain regions inside it. So that regions can have blocks. So for Openmp, while extending this, what we have to do is to have a callback to convert block, so that the region inside the Openmp operation is also converted to LLVM-IR. So I've just shown a bit more code for the convert Openmp operation inside the translation module. So this function basically takes in an operation as well as an LLVM-IR builder. It creates an Openmp IR builder if it does not exist. And then there is a switch statement, which depending upon the type of the operation, calls the Openmp IR builder. So if it's a barrier operation, then the create barrier function is called to create that barrier operation. So this slide shows just another example. So what we have on the left-hand side is an LLVM MLIR function, which has an Openmp barrier inside it. And on the right-hand side, what we see is the LLVM IR that is generated for it. And you can see the call to the barrier function inside that. So now we come to the status of this work. So the way we are implementing this is that we would like to go vertically construct by construct wherever possible. But it's often the case that a lot of these things are already implemented. But whenever we try to start on a construct, we see whether we can take it all the way from parsing down to LLVM-IR generation. So I just want to stress that this is all, there are a number of partners involved in this project. So there are engineers from NVIDIA, AMD, Argonne National Labs, Oak Ridge Labs, LAML, Barcelona Supercomputing, and ARM working on this project. So this slide basically gives you a brief overview of what everyone is working on currently. I'm not going to go into the details of this. The final slide that I have for today is how to get involved if you're interested. So most of the project management for this work is done via Google Docs spreadsheet. The spreadsheet was initially started just for the Openmp IR builder, but subsequently we have added sheets for all the stages of the Openmp compilation flow. Most the entries are as per the Openmp 5 standard, and there are separate sheets for all the stages. So if you go, there's a pointer I have placed in this slide. So if someone is interested in looking and understanding the status of this project, you can just go to this link. We also have weekly meetings for this project on Thursday around 4 p.m. UK time, where we discuss the status of this project, any blockers, and things like that. I've also put a pointer to the minutes and agenda for this. If anyone is interested, you can let us know and we'll let you know how to join. Yeah, that's all what I had. Thanks.
Thank you very much.